The fisheries and aquaculture sectors have been increasingly recognized for their essential contribution to global food security and nutrition in the 21st century. Further expansion of this contribution requires the acceleration of transformative changes in policy, management, innovation and investment to achieve sustainable and equitable global fisheries and aquaculture. Rainbow trout, Oncorhynchus mykiss, is one of the most widely cultivated fish species in European aquaculture due to its adaptability to various freshwater environments and its economic value. The species was originally native to North America but has been successfully introduced and bred in many regions of Europe. The production of rainbow trout in Europe has seen significant growth, driven by increasing consumer demand for high-quality, locally sourced fish. As of recent years, annual production figures for rainbow trout in Europe have often exceeded 100,000 tons, making it a critical component of the aquaculture industry. Italy is one of the leading countries in rainbow trout production within Europe, with significant aquaculture activity concentrated in regions with abundant freshwater resources, such as Lombardy, Trentino Alto Adige, and Emilia-Romagna. The reproduction of rainbow trout is well understood, and the techniques are well developed. The dry method of fertilization without admixture of water is the most common approach. Eggs are removed manually from females, under anesthetics, by applying pressure from the pelvic fins to the vent area. Up to 2,000 eggs per kilogram body weight are collected in a dry pan and kept dry, improving fertilization. Males are stripped in the same way as females, collecting milt. Milt from more than one male ensures good fertilization, is then mixed with the eggs. Water is added to activate the sperm and cause the eggs to increase in size by about 20% by filling the paravitelline space between the shell and yolk, a process known as water hardening. Fertilized eggs can be transported after 20 minutes and up to 48 hours after fertilization. High mortalities of embryos produced under intensive hatchery conditions are often caused by various husbandry acute, e.g., handling and disease, and chronic, e.g., poor water quality, confinement, overcrowding, stressors during incubation period in large-scale hatcheries. High rates of bacterial and fungal infection can result in the discard of whole egg batches, including healthy embryos, representing the main gap within the supply chain. Since oomycetes species like Cyprillenia sp. are able to colonize surface of the dead eggs but also to suffocate the surrounding living ones, a constant and quick identification and removal of infected eggs is necessary. In fact, this step is characterized by the higher percentage of loss compared to the other steps. Delta is approximately 20%. The management of fungal and bacterial infections has historically relied on the use of chemical treatments which may have negative effects on human and environmental health. Fast and automatic identification and removal of whitish dead eggs in early developing embryos is needed to reduce microbial spread and avoid early food losses deriving from the whole batch discard. In this context, the T3.4 of FOLOU project aims to development and validate an automatic system based on multispectral cameras that will be used to precociously identify, remove, and count dead embryos. The device has been set up carefully by the UNIVPM staff at the trout facility close to Trento, Italy, to test its efficiency in the farm environment. A cochlea is used to gently lift the embryos, allowing the vision system to analyze them individually and accurately. The helix has an adjustable speed to ensure that the embryos are exposed to the cameras for a sufficient amount of time without causing physical harm. Once analyzed, the system can perform an automatic action, separating healthy embryos from sick ones, thus facilitating the management and selection of viable embryos. Additionally, the system has a real-time monitoring. Thanks to the probes and vision system, it is possible to continuously monitor both the embryos and the environmental conditions, ensuring an optimal environment for embryo development. The combination of high-quality cameras, powerful deep learning models, and the environmental monitoring system makes the system extremely efficient and precise, optimizing the success rate of the embryo incubation process. This device could improve up to 5%, but reaching 20% considering data from some publications. the number of eggs that pass the step 3 and achieve the eyed stage, less delicate, thus improving the productivity of the farming. This would lead to an increase, for example, in Italian rainbow trout production of 1,723 tons and of 9,190 tons at European level.